Hello again, everybody. After discussing the hypothesis testing, we do need to take an overview about the chi-square distribution and the analysis of the frequencies. First, you do need to know that chi-square is a statistical analysis procedure that used for certain cases of analysis, not all of them. It cannot be used for quantitative variables, but used in the frequency table. It can be used for the counts. If you have counts, for example, or percentage in certain population or certain treatments, it can be used directly. So the chi-square distribution, as long as I remember that we discussed something related to chi-square, if you remember the observed and the expected frequencies or the counts in the class, and we have solved, I think as long I remember that we solved two problems related to the chi-square in the class. So now we return back to discussing it in some details, but briefly actually. We'll not go in deep details, and just to know those information related to the chi-square distribution. Now we have something called the mathematical properties of the chi-square. The chi-square has certain properties that should be followed actually, and you should be follow it in order to be able to characterize that it is a chi-square distribution or not. Now we do need to suppose that we want to select a sample of size n from normally distributed random variable y within a mean of mu and variance equal to sigma square. Each value can be transformed to the standard normal variable z. And as you see here, we are discussing everything related to the chi-square, and this chi-square is very important. You do need to know that we are just having the normal distribution cases because we actually discuss it in details, and I think that you got the point or the information that you need from the distribution of z or t. So our assumption here is we have a random, normally distributed random variable, which is y. We have a sample of size n that is drawn from large population of mean of mu, as you learned previously that we have the mu is the mean for the whole population mean in general, and sigma square is the variance of this large population. Now, in this case, if we have those samples of n number and y of mean, we do need to convert them to or transform them to standard normal variable by using the normal equation that has been used previously or widely of z equal to yi minus mu over sigma. So each value may be squared. Each value here may be squared as z square, and we will find it follows the chi-square with just only 1 degree of freedom, and as follow. And as you see from the second equation right here, or formula, which is x squared, it is abbreviated or simple use for the chi-square, which is x squared equal to yi minus mu over sigma squared, actually yi minus mu squared actually over sigma. This is the general formula for finding the chi-square, and as you see from here, we have the degrees of freedom, which is just only 1 degree of freedom. And if you return back to my lecture, you can find how can we use the degrees of freedom and why do we need those things, and we dealt with them actually in the class, and also the table that contains the degrees of freedom. And I told you that the degrees of freedom usually n minus 1, the number of observations minus 1, and this tells us the number of comparisons that can be made between the treatments that we are dealing with. For example, if we have just only 2 treatments, we can just only compare the first with the second, and also the second with the first. So we have just only one independent comparison. This is the first one. If you have three treatments, for example, it means 3 minus 1, it will be equal to 2. And this is why how many independent comparisons that can be made from between the treatments are. And if in the case of 3 treatments, we can compare the first one with the second, and the first one with the third. So we have 2, and the third. This is the first case. And if we are gonna compare the third with the others, the third with the second, and the third with the first. So we have 2 comparisons, and the same for the second treatment that can be compared with the first and also with the first. So this is the term behind why do we subtract just usually 1 from the degree from the total number of observation in case of the degrees of freedom. So it is the independent comparison that can be made between the treatments. So we have chi-square is abbreviated or simple for use x square for the chi-square, and this is the first formula for finding the chi-square. And as you see here now, we do need to suppose that we randomly independent select sample of size n equal to 2. For each sample, we can transform each value of y to standard normal value z square, which is, as you see, for both of them, if we have 2, for example, y1 minus mu over sigma square plus y2 minus mu sigma over square over sigma. It means that we can also transform both of them, the first and the second. So chi-square will be equal to the summation of the deviation of the first sample from the overall mean over sigma, and the second minus the overall mean of the population over sigma. And it can be here abbreviated for the first y1 minus mu over sigma square by z1 square, and for y2 is z2 square, just only to facilitate your to guide you, just only to understand it in a simple way. So in repeated procedures for any n size of samples, actually the sum of the results or resulting z square will be distributed as chi-square within degrees of freedom. And in general, you can see chi-square x square, which is chi-square here, equal to z1 square plus z2 square plus z3 square up to zn square. So this is the general formula for finding the chi-square. So the chi-square distribution with n degrees of freedom will be equal to the f u equal to 1 over this component, and here we use u in the denominator, as you see, which is u should be greater than 0. Should be greater than 0. And now we'll go to discuss details related to the properties of the chi-square. So as you see, it is the first or the 5 points here. As you see, E is abbreviated for the previous equation. K is the number of degrees of freedom. U, X, and usually all of them are squared. Mean and variance of chi-square distributed are, as you see, and the shape of chi-square distributed for several values of K. We will go to the shape of it and the other things. So we'll go directly now to discuss the observed, which is very important, the most important thing here, the observed versus the expected frequencies, which is very important to be known right here in chi-square analysis. The chi-square statistic is most appropriate for use with categorical data or variables. As I told you, categorical data, the frequencies, okay, or categorical data, the quantitative trait data used in form of frequency. If we use, I told you that we cannot use it for the quantitative traits or variables. Just only we can we can use them just only in one case, by converting the quantitative traits to categorical data or to frequencies. In this case, it will be it can be used actually in the as chi-square case. So there are two sets of frequencies in this case, two sets of frequencies to return back to how can we, in the cases that can be used, that allow us to use the chi-square, the counts, the persons, and the quantitative variable. Just only you do need to convert it into categories. This is the third thing. Okay, the third case. If you convert the variables or quantitative variables into frequencies, categorical data, the chi-square can be used for such analysis. So observed frequencies and expected frequencies. Observed are the number of subjects or objects in our sample that fall into the various categories of variables of interest. This is the observed. So the observed are the number of subjects or objects in our sample that fall into various categories of the variables of interest. So the observed thing, from its nomination, it is the observable or the observed values that it is a tangible thing, it's a calculated thing, you can find it. It's totally different from the expected. So if you, for example, if we have a sample of 100 hospital patients, we may observe that 50 are married, 30 are singles, 50 are widow, and 5 are divorced. So this is the observed variables. So we have 100 hospital patients. We categorize them according to the marital status actually. We find 50 are married, 30 are singles, 15 are widow, and 5 are divorced. So this is the observed. We count them actually. We count those patients to be distributed in those 5 or 4 categories. This is accountable thing. So, but the expected frequencies are the number of subjects. Like if we use the null hypothesis that 4 categories of marital status are equally represented in the population. In this case, we will expect our sample to contain 25% of 25 are married, 25 are single, 25 are widows, and 25 are divorced. How can I facilitate or give you the expected chi-square, expected frequency? In a simple way, we can say that if you go, we suppose actually in general, if we go to certain hospitals, in our example right here, we expect the patients that are found in the hospital to be equally distributed to the 4 categories of the marital status. So if they are 100, okay, we expected 25% from them to be divorced, 25% are married, 25% are singles, and 25% are widows. Okay, so in this case, if we multiply the 100 by 25% for example, the married patients, okay, we expect to have 25 married individual. And if we count 100 by 25%, it means that we will get 25 patients of singles and so on for the other. So the expected thing is totally different from the observed. Now I assume, for example, another example, if we go for example to the just Jordan University of Science and Technology population, and we do need to count or to know the sex ratio, that found in this university. We expect them to be equally distributed, 50% for the females and 50% for the males. And in this case, if the total population or the total number of students found in the university or at the university to be, if there are 1,000 for example, we expect to find 500 from the males and 500 are to be females. This is the expected thing. But if you go directly to count them at the university or in the campus, okay, you will find something different. For example, we may find 700 females and 300 males, or the opposite. This 700 and 300 that we found at reality and in the real status, okay, this is the observed. But the expected will be 500 males and 500 females. And this is the general understanding for the chi-square expected and observed categories. So if you have any case, you do need to know the expected values before commencing in solving the chi-square problem. This is in general, and I hope you got the point. The chi-square test statistic here, the test statistic for the chi-square in general that has been also discussed in the classroom, which is chi-square x square, which is chi-square equal to the summation of OI minus EI square over EI. The OI here is the observed, the summation of observed minus the expected square over the expected. This is the general formula for finding the chi-square values. So OI is the observed, EI the expected, K right here, it is K, you can find it over the summation. The summation here is the number of groups for which expected and observed frequencies are available and are, which is below the number of constraints or restrictions imposed to the given comparison. It can be put here in the summation R and K. Only the sufficiently large values of x chi-square will cause the rejection of the null hypothesis. So the expected values from this thing, okay, from this formula, it will be a value. This value called the chi-square value, and this chi-square should be large enough to reject the null hypothesis. You do need to return back to the hypothesis testing lecture. What do you mean by the null hypothesis? If the chi-square is very large compared to the tabulated chi-square, it means that we can reject the null hypothesis. It means there is a significant differences between the observed and the expected. By the way, chi-square value, this is the general formula for finding the chi-square value, calculated chi-square value, and we have a tabulated table which is called chi-square table that consisted of rows and columns and many values actually. The first column, it is what we call the degrees of freedom that has been discussed in the last or the previous slides, okay, and also we have significant level, okay, 0.05, 0.01, and the other thing. So if you have a degrees of freedom, and also if you have the confidence level that you are working for, which is 95% or 99% or 1 minus alpha, whatever that the significant level that you will go to the degrees of freedom. There is specific values in the table. You do need to compare it with the calculated chi-square value that resulted from this formula. If this formula or the result of this formula is larger than the tabulated chi-square value, you will reject, okay, the null hypothesis, and you can conclude that there is significant differences between the observed and the expected values of the treatments. And also the computed value of a chi-square is compared with the tabulated value. I stated in here, okay, of chi-square K minus R degrees of freedom. It is the decision is reject the null hypothesis if it is large, okay. If it is larger than the tabulated, we can say that we will reject the null hypothesis of the chi-square if the chi-square is greater or equal to the tabulated chi-square for the chosen value of alpha prime. This is how can we deal with chi-square values and how can we compare them with the tabulated chi-square value. If the chi-square value is large, that resulted from this equation, observed minus expected square over expected, larger than the tabulated one by using the degrees of freedom K minus R, okay, we can conclude that the null hypothesis will be rejected and will accept the alternative hypothesis. That means that there is an existed significant differences between the observed and the expected, and we can conclude significant differences between the treatments. Now I have an example right here. I add actually the frequency table. Actually, the frequencies, as we discussed previously, it is just only continuation in our discussion. Example, we have inpatient ratio, and number of hospitals. So this example is dealt with number of hospitals. We go directly to those hospitals and we count the inpatient ratio. The inpatient ratio in different hospitals. So the first category, that is from 0 up to 39.9 inpatient, okay, we found 16 hospitals that fulfill this category, and the second category is 40 up to 49.9, we find 18. The third is 22, which is 50 up to 59.9, up to 100 to 109.9 inpatient ratio. We found 4 hospitals that with this ratio. So we wish to know whether these data provide sufficient evidence to indicate that the sample did not come from normally distributed population. So we are dealing, it's a continuation actually, frequency table, and we will deal with the normal distribution, whether they are normally or not. So again, we wish to know whether these data provide sufficient evidence to indicate that the sample did not come from normally distributed population. Now, how can we solve such problems? Now we do need to see the data. You can go to the data, see the table, the previous table, the categories, and usually you find raw data, and you do need to formalize them in a certain frequency table, and the results are indicated in the previous table. So our assumption here, we assume that the sample variable are a simple random variables. This is our sample from what assumption? From where? From the question, from the table. So we do need to indicate our hypothesis, the null hypothesis, and the alternative hypothesis. So the null hypothesis here, the population is normally distributed. Our assumption, it is normal. Sample are simple random variables. Okay, our assumption here is it is normally distributed. As you see, as we indicate in the hypothesis testing lecture, you will see that there is no differences. Usually null hypothesis, no differences, they are normally. The alternative hypothesis is not normally distributed. The opposite, usually the opposite of the null hypothesis. And I argue to return back to the lecture, the hypothesis testing lecture. Okay. Now, the test statistic that to be used here, just only is the chi-square, okay? Chi-square formula, which is summation of observed minus expected square over expected, okay? The fifth step is distribution of test statistics. If the null hypothesis is true, the test statistic is distributed approximately as chi-square with k minus r degrees of freedom. And the sixth step is calculation of the test statistic. We do need to calculate it. We need to know the mean and the standard deviation. In this case of the samples, the mean and the standard deviation are 69.91 and this S, which is standard deviation, 19.02 respectively. And if you return back to the frequency table lecture, you can find that I gave you how can we calculate the mean of from the frequency table. Okay, and I gave you how can we calculate the variance, okay, of the frequency table. So you can easily obtain the standard deviation and the mu. And why we use this the mean, because we are dealing with the normal distribution, and we will use the z values just only directly to approve whether it is normally distributed or non-normally distributed. And the next step is to obtaining the class interval of the frequency of occurrence of values that we expect when the null hypothesis is true, and as follows. Now we do need to have the expected and the observed. As you see, the expected is much more important because the observed are there in the table. So we do need to determine the expected relative frequency of occurrence, then multiply them by the total number of the values to determine the total number of values to obtain the expected number of the values for each interval. This is how can we obtain them. Okay, just only to obtain the expected relative frequency, and I told you how can I teach you actually how can we obtain the relative frequency. Example, we will use the formula for xo minus mu over sigma. This is how can we find them. In case of finding the expected relative frequency of occurrence, 40 minus for example 40, the category 40 up to 49.9, the z-score or value corresponding to x is 40. Okay, z equal to 40 minus the mean over sigma. The mean, as I told you previously, it is 69.91 over the sigma standard deviation here 19.01. It will yield minus 1.57. The z value for corresponding of the x is 50. When x is 50 is 50 minus the mean over the sigma, and it will yield minus 1.05. This is the normal procedure to find the corresponding z values. In the table D, if you return back to the textbook that I have uploaded in the e-learning system, we have table number D, called it D. We will find the area to the left of minus 1.05 is 0.1469, and the area to the left of minus 1.57, sorry, that has been derived from the previous equation is 0.0589. This is those values 0.1469, 0.0582 again, they are derived from the table, okay, that corresponding to the left of minus 1.05 minus 1.57. Those two values have been derived from the equation, which is x minus mu over sigma. Return back to the previous slide. The area between minus 1.05 and minus 1.57 equal to 0.1469 minus 0.0582, which yielded 0.0887, which is equal to the expected relative frequency of the occurrence. That means that if the ratio value normally distributed, we expect 8.87% of the values between 40 and 49.7. This is just only for one category, and you do need to repeat those steps for all the categories. Again, you do need to repeat them just only to obtain the expected values, okay, and compare it with what? With the relative frequency. So when multiplying this value 0.0887 by 250, the 250 is the total number of hospitals, okay, we find the expected frequency for the interval to be 22.18, and so on for the other intervals. You do need to return back and calculate all those values to the rest of the categories, so you will obtain the expected from the frequency, relative frequency, the expected. So you do need to use the z values formula, x minus mu over sigma for each category, the lower limit and the upper limit, okay, and you will find the area below the curve from the D table, okay, and then you do need to compare them, multiply the resulted values by the relative frequency to obtain the expected value. So we have the observed that has been calculated directly in the hospital, and we can find the expected by multiplying those values by what? By the total number of observations that are used in the example. Now, as you see, this is the final table, and you can train yourself actually. How can we obtain those numbers? Inpatient, which are less than 40, the expected relative frequency will be 0.0582, and the expected frequency is 14.55. Okay, just multiplying by using the previous steps for the category. The second category, it will be 22.18. The third category, which is 50 up to 59.9, 38.65, and so on for the other for all the other hospitals. And you see here it's the total 250 hospitals, and you can see the relative frequency is 1, just only to calibrate your answers, and you can detect it whether it is true, or if you have, for example, some problems in the calculations, just only add the expected relative frequency, all of them should be equal to 1, and the expected frequency that you calculate, just only the summation of them will be 250. Okay, this is the expected frequencies, and the observed and the expected frequency, just only number of hospitals. For the first category is 16, 18. This is the countable thing that have been counted directly, and we have the expected from the previous steps, and you can calculate in the last column here, as you see, observed minus expected over expected. Observed minus expected square over the expected, just only it will yield the first category, for example, 0.145. From where we get this value, just only observed, which is 16 minus 14.55 square over 16 over 14.55, sorry, over the expected. So it will yield 0.145. Again, 0.145 here in the last column, the first value resulted from observed minus expected square over the expected. So the observed here is 16. You can find it in the table, in the first table actually. The expected frequency, the second, the expected, the third, from the third column. Those values came from the previous calculation of the normal distributed and the surface below the curve, and we found them by using the previous steps. So 16 minus 14.55 square over 14.55 will yield 0.145. For the second category, 18 minus 22.18 square over 22.18, it will yield 0.788, and so on to the rest of the categories. And the summation of all those observations will equal to, as you see here, 25.854. This is the summation of OI minus EI square over expected. So the chi-square value is 25.854. This is the value that to be compared with the tabulated chi-square value in order to judge or to have a decision on whether to reject or accept the null hypothesis. From the table, we can see the chi-square value equal 25, as you see previously, 0.854. The appropriate degrees of freedom here are K minus R, which is 9 minus 3. We have 9 minus 3. Number of sections make sum of observed of expected. Sum of expected, mu and sigma equal to 6. K is the number of groups, and R is the number of parameters estimated for the data to compute the expected frequencies. Okay, in this case you do need to understand the K values and the degrees of freedom. So we have three degrees of freedom. So we have R is the number of parameters estimated from the data to compute the expected, and you can see the K is the number of groups, that we have, that are 9 actually. So the statistical decision, we will find the tabulated X using 6 degrees of freedom, which is the result 9 minus 3, okay, which is 0.05 level of significant. We use it actually the significant level or the confidence level. From the table, Fx, it will be equal to 18 point, from the table directly, 18.548, it is from the table, directly from the table by using 6 degrees of freedom and the expected significant level. And this 18.5 is smaller than the value that has been calculated for chi-square, and then, as I told you, if it is large enough or larger than the tabulated chi-square value, it means we will reject the null hypothesis, and the samples came from the normally distributed population. The conclusion is it is normally distributed population.